Here we're going to work on applying the state space representation. So that is, given some system, come up with the state space representation. And the first step is to define the state vector, x, which is a vector made up of the state variables. And the approach that we're going to take is to start with the differential equations that govern the system. And so if it was an electrical system, we could use Kirchhoff's voltage law to get the differential equations. And we're going to choose state variables from those equations. And each state variable is going to be one of the variables that has a time derivative in the differential equation. So we'll look at the differential equation, the variables with time derivatives, and those will decide what our state variables are. And so our goal is to transform an nth order differential equation into n first order differential equations. This means that the number of state variables is going to be n for an nth order differential equation. So if we had a spring mass damper system, which would be a second order differential equation, we'd have two state variables. And what's implied by this is that we can have more than one state variable from just one differential equation. And I mention that because it's different from modeling in the frequency domain, where we had the number of equations was equal to the number of degrees of freedom, or independent motions, in the system. Here we could have just one motion, but still have n first order differential equations. And whenever we're choosing the state variables, they have to be linearly independent. So for example, here's a state vector x, bold indicates it's a vector, and it's made up of the three variables, x1, x2, x3. This state vector is not valid if, for example, x3 is equal to 5 times x1 plus 4 times x2. That means that x3 is some linear combination of x1 and x2. So that's a requirement for the state variables. They all have to be linearly independent. You must not be able to write an equation giving a value for one of the state variables as a linear combination of the others. Now on to some examples of state space applying state space. So here is a spring mass damper system, and we want to choose state space. So we've got a damper connected to ground, to a mass, a spring, another mass, and we have an external force applied. And we'll just say that the interface between the masses and ground is frictionless. So we have frictionless right there. So we want to start with the differential equations for the system. So let me just draw the free body diagram for the masses. There's x1, and we have c times x1 dot, k x1 and k x2. And then for the other mass, m2, we have the external force, we have kx2 and kx1. So now the equations of motion will give us our differential equations, and we get that m1 x1 double dot plus cx1 dot plus kx1 minus kx2 is equal to 0. So there's our first differential equation. And the second differential equation, we have negative kx1 plus m2 x2 double dot plus kx2 is equal to f. So we said now we need to choose our state variables, and I said that we're going to choose those based on the variables in our differential equations that have time derivatives. So x1 has a time derivative, x1 dot, and x1 dot has a time derivative, x1 double dot. So we have state variables, x1 because we have time derivative of x1, and we also have x1, a time derivative of x1 dot, so we'll call that v1, and x2 has time derivative, x2 and v2. So now we can write our state equations. And if you remember, the form, the standard form, is your state vector. Time derivative of your state vector is a times x plus b times u, where u is the input. So we'll write these equations for our state. We'll write this equation for our state variables. So x1 dot is v1, and v1 dot, which is x1 double dot, is negative k over m1 x1 minus c over m1 v1, which is x1 dot, plus k over m1 x2. And then we have x2 dot is equal to v2, and v2 dot, which is x2 double dot, is equal to k over m2 x1, just rearranging this equation, plus k over m2 x2 plus f. Okay, so now we can put these four equations into this matrix form here. So we have x bar dot is equal to, so now we need our coefficient matrix. So we've got 0, 1, 0, 0 for this equation, negative k over m, I wrote this too small, but negative c, k over m1, negative c over m1, and k over m1. Let me scribble this one out, make another column. Okay. And v2 is not in this equation, so 0 there. And x2 dot is equal to v2, so 0, 1. And v2 dot is equal to k over m2 times x1, nothing of v1, k over m2 times x2, and nothing of v2. So here's our state vector, x1, v1, x2, v2. And now the input. So the matrix B is just 0, 0, 0, 1, and the input is f. So our state space is the 4D space made up of these variables, x1, v1, x2, and v2. And this is the state equation. So given this system, we found the state equation. And now we'll do another example with a mechanical system. Again, we want to choose a state space, and on this one we're going to find some output, which is going to be the spring force. So the force from this spring on the mass. And, there's also an applied force here. So the free body diagram, we have M, there's F, and K x1, K x2. And in the free body diagram at x2, we have K x1, K x2, and C x2 dot. So we'll get two differential equations from these. So we have that M times x1 double dot plus K times x1 minus K times x2 is equal to the applied force F. And then we have negative K times x1 plus C x2 dot plus kx2 is equal to 0. Alright, so we've got this second order differential equation and this first order differential equation. And we need to choose our state variables. And they're going to be the variables in these equations that have time derivatives. So x1 has a time derivative, and then so does x1 dot. So x1 and v1. And then x2 has a time derivative, x2, but x2 dot doesn't have a time derivative. So we have 3 state variables for this system. And we can write our state equations here. So x1 dot is equal to v1, and v1 dot is negative k over m times x1 plus k over m times x2 plus f, plus 1 over m. Oh, that makes me think I made a mistake in the previous one. Let's check. Yeah, this should be plus 1 over m2. Because I forgot to, I divided everything by m2 over here, so this should be 1 over m2. And this should be 1 over m2. Okay, just got in a little hurry there. So in this equation, when I rearranged to get v2 dot on the left-hand side, I divided through by m2, but forgot that whenever it was a coefficient for f. And so the final equation is going to be x2 dot is k over c times x1 minus k over c times x2. Okay. So we could put that into matrix form. The time derivative of our state vector is 0, 1, 0. Our state vector is x1, v1, and x2. And then we have negative k over m, 0, k over m. And the input is 0, 1 over m, 0. Well, the input matrix is that, and then input is f. And our third row, x2 dot is equal to k over c times x1, 0, negative k over c times x2. So now we have the A and the B matrices. And we also wanted to find some output from this. So we need an output equation. We want to find the spring force. And so what that, we could just redraw the free body diagram for the mass. We'd have the applied force, and then we'll show the spring force, F of k. And we'll define positive being right. So F of k is equal to k times x2 minus x1. So if shown in this direction, that force is going to be the spring constant times the difference between x2 and x1. And this is k, or negative k times x1 plus k times x2. So we can write our output equation. Y is, and in this case it's not a y is not a vector, it's a scalar. It's the spring force. And here's the output matrix C, so it's negative k, 0, k, and then multiply that by the state vector, x1, v1, k2, x2. Right? So that's the state space representation for this system, or a state space representation. It's not unique. But here's the state equation and the output equation. And finally, an electrical example. So we have this RLC network, and we need to write the differential equation. And so we're going to use Kirchhoff's voltage law and say that the sum of the voltages around this loop is 0. But we're going to use the voltage-charge relationship for these elements. So those relationships are that the voltage across the resistor is R times dq dt, and the voltage drop across the inductor is L times the second time derivative of Q, of the charge. Charge being the charge flowing through a cross section of the wire. And the charge across the capacitor is 1 over C times Q. I'm sorry, the voltage across the capacitor. And those all add up to the input voltage. So there's a differential equation. Okay, so our state variables are those that have time derivatives in this differential equation. So we've got Q because we have Q dot, or time derivative Q, and then Q dot has its time derivative. And so our other state variable is going to be Q dot, which is equal to the current. So our state variables are the charge and the current. Alright, so now we can write our state equations. We have first that Q dot is equal to I, and then this looks kind of funny, but I dot is, so it just comes from rearranging this equation. We have negative 1 over LC times Q minus minus R over L times I dq dt plus 1 over L times VI. So now we have the derivative of our state vector in terms of the state variables and the input. So we can write this in matrix form. This time derivative of the state vector 0, 1, negative 1 over LC, negative R over L. That's the A matrix. QI plus 0, 1 over L times the input voltage. Okay. And we're also, so there's the state equation. We're also asked to find the element voltages. So we want the voltage across the resistor, the voltage across the inductor, and the voltage across the capacitor. The voltage across the capacitor is just given by the voltage-charge relationship. So VC is 1 over C times the charge. And the voltage across the resistor we get from Ohm's law is just the resistance times the current. And the voltage across the inductor we can get from KVL, and that's, or Kirchhoff's voltage law, and that is, so that says that the voltage across the resistor plus voltage across the inductor plus the voltage across the capacitor equals the input voltage. So voltage across the inductor is negative VC minus VR plus VI, but we need these in terms of the state variables. So just substituting in from up here, we have negative 1 over C times Q and negative R times I plus VI. So now we can write our output equation. And here we have an output vector Y. Oops, that's not a Y. Y is equal to, and we're going to have a 3 by 2 matrix here. 1 over C, 0, 0, R, and negative 1 over C, negative R. So if we multiply that matrix, which we call C, capital C matrix, times the state vector, which is just 2 by 1, q and I. And also include input, because there's input in this equation, so we have 0, 0, 1 times vi. So our state space representation is made up of the state equation and the output equation. So the time derivative of the state vector is given by this equation, and the output vector is given by this equation. So this video just showed some practice in applying the state space representation to different systems. We'll get to solving these equations and designing controllers later on.